All right. So good afternoon. Welcome to session 439, Enabling Multi-Tenancy and Converged Fabric for the Cloud Using Quality of Service. I'm Charlie. I'm a program manager for QoS for Windows networking team. This is Richard, my partner, and he's developer lead for QoS. So I see many of you probably attend the session on Hyper-V network virtualization and the session on designing the building blocks for Windows Server 8 Cloud. Yes? So for this session, we're going to remain on the same subject, but we're going to talk about some specific challenges in the data center where businesses are required to provide predictable network performance and SLAs. We'd like to share with you how we address these challenges and more importantly, get your feedback. So just a reminder, this is one of the Windows Server 8 is optimized for the cloud series. And with that, I'll hand it over to Richard.
All right. Thank you, Charlie. So here's a picture of the freeway between whatever airport you flew in and this convention center. It's not really, but that's what they look like around here. And if you look at this picture, you might have to wonder about that ambulance and think, man, I'd be in a bit of a panic if I were in that ambulance trying to get to the hospital right now. Probably as an engineer, you should look at this picture and think, if I were designing a freeway infrastructure, how would I make it so an ambulance can get to the hospital in a timely fashion? And you might come to two conclusions, both of which have problems. The first way you might try to do this is to add a lane. There's two options there. You could add a lane and cordon it off just so the ambulance can go down it. But the problem with that is now you're paying for a bunch of pavement that's hardly ever getting used. And then you also have a bunch of people driving by in this congested freeway looking at that empty lane very suspiciously. So the other option is you say, I'll just add some lanes and make the congestion go away. But historically, that's never worked, as anybody who lives in a metropolitan city knows. Unfortunately, this is exactly what we do in data centers today. Here's a simplified diagram of what an endpoint in a data center might look like. You have multiple tenants hooked up through a Hyper-V extensible switch. You have some management OS workloads in the root, and they're all going out some network interface. And surprise, surprise, everybody's trying to go out that network interface, you get congestion. And you think, all I need to do is add more lanes. So you add a whole bunch of NICs, add a whole bunch of hardware. Well, this is not super satisfactory because your tenants are all complaining because they're all congested on this link here. And in the meantime, just like in the freeway analogy, you've got your ambulance traffic. Let's say that's your management traffic. It's using up a whole NIC that you're paying for cabling, you're paying for a port on a switch, and it's hardly ever getting used. So you think, well, I'll just add a big NIC. That's great. I've heard these things are great. I've got 10 times the bandwidth now. Well, there's an old maxim that software expands to fill all available resources. And so this connection between your extensible switch and this 10 gig NIC heats up. And look at that. It looks just like the first picture. Your management traffic can't get through because all your tenants are chewing up all the bandwidth on that NIC. So over-provisioning doesn't help you do anything to enable multi-tenancy. It just costs you money. And I think everybody agrees that, by this point, over-provisioning is a solution of the past. So Windows Server 8 has a couple new features to enable multi-tenancy and enable you to converge your fabric using QoS in the system. So I'm going to hand it back over to Charlie, where he's going to do a demo showing how you can enable multi-tenancy on a Windows 8 server.
Okay, thanks, Richard. So for this demo, just imagine you're a hoster. So you are providing hosting services to your customers. And one day you get a phone call from a customer, and he's not happy. And the reason he's not happy is because the connection to one of his servers is really slow. So to explain to you what he means by slow, he just copied a file from his server to, let me bring up the right window, to copy a file from one of his server to a remote file server. So this is his server, which is a VM on your data center, on a Hyper-V in your data center. So you can see, this is not really going very well, isn't it? It will take about 4 hours. So this throughput is definitely much, much slower than you and your customer ever expected. So what's really going on? What's going on is really on the Hyper-V, there are 3 other VMs are actually also running. They are hitting the network really, really hard. Now, because you don't have any policy on this Hyper-V, these 3 VMs, VM2, 3, 4, are actually slamming the network and taking away the bandwidth and starving this VM1. Now, with Windows Server A, you have 2 ways to do this, to provide the network performance isolation for a VM. One is the maximum bandwidth, which you probably have seen the demo in the Hyper-V networking deep dive talk yesterday. Now, for this one, I'm going to show you the other one, which is the minimum bandwidth, and how minimum bandwidth work. And you can see, actually, the throughput is actually only 5 megabytes per second. So I'm going to bring PowerShell. You probably should be familiar by now very much. I'm going to apply, I'm going to apply a fair sharing policy. So essentially what this policy does is just to make sure all the VMs can fairly share the bandwidth. Now, if I go back to this diagram, and you can see this VM, the throughput is just ramping up. So let's take a quick look at this script. This is a very simple script. It only has 4 commands. The commands basically just assign an equal weight, a weight of 1 for each of these VM. Now, this Hyper-V is actually on top of a 1 gig link. Now, 1 gig link is about 125 megabytes per second. We have 4 VMs. So essentially, you do the math, it's pretty much each VM should have about 30 megabytes. So that's exactly what this VM is trying to do. It's ramping up because of TCP. It has a congestion. Now you have a policy. It's ramping up. So it's ramping up around above 25. So this is good. But let's say this VM is important to your customer. Your customer actually is willing to pay a premium to get a better service for this VM. What can you do? Well, you may have guessed. You can actually assign a larger weight to this VM. So let's just do that. So instead of a fair sharing policy, let's apply the weighted fair share policy. So once you apply this policy, let's back to the throughput again. You can see the throughput just goes up. It continues going up. And if you look at the weighted policy, no surprise, we just assigned a big weight to VM1. Instead of 1, it has a 5 now. So far, so good. So the question you may have by now is, well, this demo looks very similar to the maximum bandwidth demo you saw yesterday. So what's the difference between minimum bandwidth and maximum bandwidth? The difference is this. Let's actually say the VMs, the other 3 VMs are not running. So to do that, I'm just going to pause these 3 VMs. Okay. So what it means is because these VMs are stopped running, well, paused, so that means there's more bandwidth available. And you can see because there's more bandwidth, this VM1 can actually take advantage of this, and the throughput goes even higher. And I can tell you, it stays here because there's a disk I/O limit. So that's the bandwidth it can get. So this is because minimum bandwidth actually can help you better utilize network resource. And Richard will actually provide more details on this. Back to you, Richard.
Thanks, Charlie. I hope you saw that it was really simple to do that with PowerShell. So let's talk a little bit about how we're enabling multi-tenancy and performance isolation here. So here's a little cartoon of multi-tenancy. You have multiple workloads for different tenants running on the same servers. And we'll talk a little bit about minimum bandwidth, what it's designed to do, how it's designed, and how you configure it. And we'll also go a little bit over maximum bandwidth as well. So suppose you have 3 services you want to host. You want to be able to enforce a bandwidth allocation on those 3 services, and you want to get performance predictability on them. At the same time, when those services aren't consuming a whole bunch of bandwidth, you want to be able to allow the other services, just like Charlie showed, to use that available bandwidth, and that gets you high link utilization. So this is the demand curve for these 3 services, and you can see in the morning at 8 o'clock, 2 services are busy, and 1 isn't. It's not doing anything. At 2 o'clock, everybody's busy. 10 o'clock, services 1 and 3 kind of slow down, but service 2 there is still pretty busy. So you assign a minimum bandwidth policy, and in this fictitious case, we gave service 1 3 gigs, we gave service 2 4, and we gave service 3 3 gigs. And what you want to happen here is exactly what will happen. In the morning, services 1 and 2 will get all the bandwidth they ask for, because you can easily satisfy that on a 10 gig link. At 2 in the afternoon, everybody's going to get the bandwidth they ask for, and you're going to saturate the link. Services 1 and 2 are not going to get all the bandwidth they're demanding. If your SLA requires that they get that bandwidth, obviously you have to have a policy that gives them that bandwidth, and you might not be able to fit all these services on one link. But if it's acceptable to have workloads run a little longer, then you get full link utilization, everybody gets the guarantee you've provided. And at 10 o'clock, you're still saturating the link. Service 2 gets all the bandwidth he needs, because services 1 and 3, they aren't using as much. Excuse me. So here's one way to configure it. This is called relative minimum bandwidth, and this is what Charlie just demoed. I apologize for making you do math, but the way this works is you apply a weight to each port on the Hyper-V extensible switch, and each VM attached to one of those ports will get a bandwidth of its weight divided by the sum of all the weights. And so I apologize again for making you do math. In this case, your critical workload here that needs tons and tons of bandwidth is going to get 5/8 of the bandwidth of whatever that NIC happens to be. So 625 or 6.25 gigs on a 10 gig link. The nice thing about this is the weights have no fixed relation to the bandwidth provided by the link, so this allows a form of oversubscription, and I'll talk about what I mean about that in a couple slides. Another way you can configure this, for instance, is if you're a hoster, and you have to have an absolute bandwidth guarantee for somebody. So for instance, you are hosting VMs or hosting web services for somebody, and you have a bronze, silver, and gold plan. You can say to that tenant, you're a bronze tenant, you get 100 megs. And for extra money, you can get 200 megs. This works just fine. However, because there's a direct correlation between the bandwidth you're providing and the link speed that you're connected to, there's no way to oversubscribe. So what do I mean by oversubscription? Well, if you're using NIC teaming to aggregate multiple NICs or provide failover, in this scenario, you can't actually guarantee that all these gold tenants, where I've changed the tenants around a little bit, all these gold tenants can be guaranteed to get their half gig of link speed here. Because, in the general case, there's no way for you to guarantee that the NIC team is going to distribute those connections evenly across the 2 NICs. So, the way this really manifests itself is when one of those NICs dies, or you yank the cable accidentally, or it fails over. Now you only have a 1 gig NIC, and there's absolutely no way to guarantee bandwidth in that scenario. So this is an invalid configuration. If you tried to do this in PowerShell with our NIC teaming solution, we would tell you, hey, you can't guarantee that much bandwidth on this team, and you'd just get an error. You would never be able to set yourself up like this. So maximum bandwidth is also useful. The Hyper-V networking talk gave a demo of this yesterday. The canonical scenario for this would be where you have an expensive WAN link coming out of your data center. So in this example, you might have a hosted VM that's exposing has a network-facing internet service, And you don't want to have it just run up a huge bill, or your customer doesn't want to run a huge bill. So you can cap the bandwidth at 100 megs or whatever is sensible for your customer. Also, if you have a unified remote access gateway that has to face internal and externally, again, if it's a costly WAN link, you can expose 2 vNICs into that VM, and you can have 1 NIC for your internet-facing traffic, put a bandwidth policy on it to cap it, let's say at 100 megs. Other NIC, internal-facing NIC, that one, you don't care how much it uses. It's your data center. You're paying for it already. So now I'd like to talk a little bit about how this works under the covers. So this is the original diagram turned on its side. We have this Wild West where we have a bunch of VMs attempting to talk through one network adapter. So we know a few things about the network adapter being the OS. The network adapter reports its link speed. But another thing it does is it tells us when it's sent a packet. So we can actually measure the time from when we send a packet, or when we tell the NIC to send a packet, and the time the packet actually completes. So we pipe this information into something we call a capacity meter. And the capacity meter just keeps track of how much congestion is on this NIC. This is kind of nice because it sort of measures whether there's anything beyond the NIC that's causing back pressure on the system. So this feeds back into a traffic meter. The traffic meter is sitting there looking at packets going through the networking stack, and it's looking at their classification. What traffic class do these packets belong to? And it determines if packets belonging to a particular classification are exceeding the capacity of the actual interface. Oops, wrong direction. That class of traffic is now marked. It's marked as exceeding capacity. And that goes back to our peak bandwidth meter. The peak bandwidth meter is also looking at packets coming in. And when it sees packets belong to a particular class that's exceeding the capacity of the NIC, they get buffered. And that will drain in a manner such that that class of traffic never exceeds what it's allowed to use. Now, we guarantee bandwidth by sticking something right up front called the reserve bandwidth meter, which will detect if a class of traffic is guaranteed an amount of bandwidth and it has not exceeded it, it gets to bypass all this buffering. Oh, there's one more thing I wanted to say about this. Blew right past it. So the good news about this is all done in software. And with software, all things are possible. This is not at all dependent on your hardware. It doesn't depend on what brand and NIC you have, what your NIC capabilities are. So that means you can have dozens and dozens and dozens of classes of traffic. And in this case, in this picture, we're talking about dozens and dozens and dozens of VMs. So you can have a high number of VMs on a server, allowing you to have multi-tenancy. They can be added and removed dynamically. We don't have to restart a network interface or anything like that to add a traffic class. And it turns out we can support dozens and dozens of VMs without using very much CPU to run this machine here. So by doing that, we've enabled you to have multi-tenancy on a Windows Server 8 machine without over-provisioning it, without paying too much for hardware. So now I'll talk a little bit about converged fabric. Actually, I think I'm going to get a drink real quick. I'll talk a little bit about what it means to converge your fabric, how we support, how you might configure it, and a little bit about the design. So here's a simple picture of your data center. You have a server there, and it has two kinds of I/O. You've got your file I/O, and you've got your network I/O. And they're likely hooked to two different kinds of switches. And those switches are likely then hooked to some infrastructure in your data center, a bunch of cables and more switches. And all of these things, and there's multiple different ways to do storage traffic as well. All of these different sorts of I/O cost money. So there's lots of dollar signs in there because there's a lot of hardware there. And so the goal everyone has these days is to try and converge this onto one fabric. And thereby you cut these dollar signs in half, save lots of money, everybody's happy. So the features we just showed you are not just to enable multi-tenancy. You can use the same features on any kind of network adapter or any kind of network interface. So here's a simple example. Back to the management OS. One way you could support a converged fabric is if you had a VLAN MUX driver or a NIC teaming driver that exposed VLAN NICs from a single physical NIC, you could apply a QoS policy to each of these NICs separately, and thereby allow your management traffic, your ambulance traffic, always would have the opportunity to get through. Another way you could do this is if you wanted to expose VLANs from a Hyper-V extensible switch or expose multiple ports from a Hyper-V extensible switch, you could do that as well. In this case, you could have all your management live migration hooked to V ports, and then your tenants are also hooked to those. So you can converge your storage and networking traffic and your tenant traffic all in the switch, and for added benefit, you can throw on another NIC there and get failover so that you never lose connectivity to your machine. So that's all software. The other thing is the industry has realized that you have to build some hardware features to make this work, and we take advantage of those as well. And I'm going to have Charlie demonstrate that. He's going to demonstrate how you can use data center bridging to do storage and networking traffic on a NIC without them competing for bandwidth.
Yes, thanks, Richard. Now, so for the second demo, again, imagine you are a data center admin. So from time to time, you want to actually shut down your machines for maintenance. But your customers are all over the world. So you need to keep your service up and running. And in order to do that, you want to take advantage of a live migration and live migrate the VMs running these services to a different physical server. So back to this, we're going to use the same setup. The same Hyper-V you saw before, and let's just live migrate VM1 to a different server. But before that, just take a quick look at the VM1. This VM is only has 8 GB memory, and the CPU actually is pretty low, 0.1%. Looking inside, let me actually stop the file copying, so just make sure there's no activity inside this VM. Now, we're going to live migrate this VM over a 10 gig link. Typically, such a small size VM, no activity, it takes only about 10 seconds to live migrate. So just keep that in mind. Okay, it's calculating. Okay, it's moving, doing something here, but it's not. It's not. Why it's not? So you can see the line migration actually almost freeze here. It's hanging here. Why is that? So actually you find out this line migration actually is sharing the storage traffic on this 10 gig link because a big pipe, you want to actually consolidate multiple workloads on this. So actually let me bring up the TS session to the backend, the file server. You can see the storage traffic actually saturates this 10 gig link. So what can you do? Well, you may have guessed. With Windows Server A, you can actually apply a QoS policy. So what I just did is actually create a traffic class, or you can think of it as a separate lane. We just create a separate lane for this live migration. And you can see, well, actually, it's even faster than I thought. The live migration just done. Remember, it was just hanging there, not making any progress. Once I apply the policy, it's just gone. It's just gone. If we bring back the TS session, you can see here, remember, it was 100% storage traffic. Once I apply the policy, there's a big chunk of the bandwidth just carved out. We are giving the bandwidth to live migration. That's why the live migration can finish so quickly. So there's one more thing I want to show you. So if I run this command, one of the thousands new PowerShell commands we introduced to Windows Server A, you can see it's actually this policy was pushed down to the NIC. This is the net adapter QoS. We pushed down the policy to the NIC. That's because the OS knows the NIC actually supports hardware QoS. And we are just create a traffic class and a separate lane for live migration. So this demo essentially shows you how you actually can converge storage traffic and the live migration on this 10 gig NIC. Now imagine what you can take advantage and also consolidate other workloads, like your management traffic and CSV on the same NIC. And you actually can reduce your cables, NICs, and the switch ports, and save your operational and the capital costs. So with that, I'll give back to Richard to the presentation.
So I'm going to take you back to this gnarly diagram for just 1 second. Implicit in this diagram, I didn't talk about, but I alluded to, is traffic classification. Obviously, for any of this to work, we have to be able to classify traffic. So another picture of a stack, we have a bunch of applications, and they talk to their I/O just like we were saying before, through WinSock or through a file I/O API. But in this case, we have them connected to a LAN mini port and an iSCSI mini port, and those are on one of these newfangled converged adapters. So that traffic classification we were doing for multi-tenancy at the beginning of the talk plugs right into the Windows network stack. It's not just for the extensible switch. We also have a DCB interface that runs in the kernel, and that talks to OEM-provided mini ports for DCB-capable adapters. Now, on top of this, what Charlie was exercising, we have a WMI PowerShell management story. And so you can apply policies, or you can apply policies that will classify traffic into multiple traffic classes. Those were the TCs that were in the PowerShell output. And you can classify it into up to eight classes of traffic. And if you look really closely, there's only 7 lines there because storage is one of the other classes. Now, also at the same time, you can push a policy into the DCB part here that allows you to tell the NIC how much bandwidth to give one of these classes of traffic. So depending on your network adapter, the network adapter determines how many classes of traffic it supports. You can have up to 8 traffic classes. Now, Windows has a great traffic classification story. We can classify traffic based on application name. So if, for instance, you never wanted Notepad to have more than 500 megabits of bandwidth, you could enforce a policy that said Notepad never gets more than 500 megabits of bandwidth. I don't know why you'd do that specifically, but you could, and you could apply a DCB policy that said Notepad class traffic doesn't ever get much bandwidth on this NIC. More likely, you do that with an actual network service. Also, this works perfectly well with SMB Direct, which was demoed at the server keynote. We have a traffic class for KRDMA. So KRDMA-enabled NICs using SMB Direct also plug into this scheme, and you can limit storage traffic that way as well. So Windows Server 8 allows you to converge your network fabric with your storage fabric and save a bunch of money and avoid, again, over-provisioning in your data center. So finally, as we mentioned, we enable multi-tenancy in the data center using traffic classification, using our new QoS minimum bandwidth policies. We enable a converged fabric in Windows Server 8, and you don't have to over-provision. We have a great management story. I hope you noticed that all these policies that Charlie was demonstrating were very simple PowerShell scripts. And they're also available through WMI if you want to make your own management tools based on those. And finally, great hardware. If you're an IHV, by creating great hardware that supports the maximum of 8 traffic classes, you'll also enable great support for QoS in Windows Server 8. And with that, I'll point at some related sessions and open up the floor for questions.
So just a reminder, we also be stationed at on the show floor. We have a booth for Windows networking. It's in the servers and the cloud section. Feel free to come to us, ask questions, and more information, white paper on QoS, how you configure QoS, all the commands you just saw will be published after the build conference. We also have, I think we also have alias. Okay,
no,
so we don't have on the slide, but essentially, if we write it down, it's WSA Cloud Net FB at Microsoft. Again, WSA Cloud Net FB. So we will be answering questions if we send the questions to this alias. Okay,
Thank you.
Thanks for coming.